Hello, I'm Alessandro Ronca from Sapienza University of Rome. I will present Efficient PAC Reinforcement Learning in Regular Decision Processes, a work by Giuseppe de Giacomo and myself. The setting we consider is the one of an agent interacting with its environment. So we have an agent on the left taking actions and receiving in response from the environment observations and rewards. Observations give an idea to the agent about what's going on in the world. And rewards are real values that the agent has to try to maximize. Indeed, we want the agent to act optimally. That means that the agent has to take actions to maximize the expected sum of future rewards. One can argue that in order to do so, the agent has to learn to predict the future under arbitrary policies. And then the question is whether this prediction can be based on the last observation only, without loss in accuracy, so without affecting the quality of the resulting policy. If so, we say that the Markov property holds. That means that each observation makes the previous ones irrelevant. In general, this property does not hold. In this case, we are in the non-Markov setting, which is the setting we consider here. To give you an idea of a non-Markov domain, consider this grid, a 3x3 grid, where the agent, pictured on the left, at each point sees only the current cell. It sees the coordinates of the current cell and the content of the cell, if any. Say that at the beginning, the agent is in cell 0, 0, and that has the possibility to move around. For example, let's say it goes right, and then it goes right again. And here it finds a closed door. And then it keeps going till it finds a button and it pushes this button. And then let's say that it goes back to the cell where there was a door, but now the door is open. To you, this might seem natural, and you probably think that the door opened because the button was pushed. However, if you show this to a Markov agent, pictured on the right, which assumes that the word satisfies the Markov property, the agent will be puzzled. Will say, well, that cannot be, because the cell contained a closed door. However, a smarter agent, like the one on the left, will say, well, it was closed, but then I pushed the button and it opened. The difference between the two agents is the fact that the one on the left can perform temporal reasoning, can understand that although that position is the same position as before, it was reached through two different histories, and that can make a difference. To formalize all of this, we consider non-Markov decision processes, which are generalization of Markov decision processes to the case where transition and reward functions are history dependent. So it's similar to a Markov decision process. We have find a set of actions, find a set of observations, find a set of rewards, and then we have transition and reward functions together with a discount factor gamma. The difference is that the transition function depends on histories, so sequences of observations, elements of a star, and the same is true for the reward function, as well as for policies and for value functions. We have to be generalized as well to histories of observations. And then we say that the policy is optimal if it maximizes the value on every history. However, these non-Markov decision processes are very general. There are no requirements on the transition and reward functions. And they are too general, they're not computationally tractable. So we look at a class of non-Markov decision processes called regular decision processes, where histories are seen through the lens of regular languages. That means we can think of histories as belonging to a regular language. And that means they can be represented through a number of well-known formalisms, such as regular expressions, linear dynamic logic of finite traces, monadic second-order logic of finite-order traces, and yet another formalism, which is the one we adopt here, which is the formalism of finite state transducers. Finite state transducer is a finite state machine that reads histories, in this case, of observations, and each point is in one of finitely many states. Then each state has associated a local transition and reward function. A local transition function is a function that for the current state and for an action gives a probability distribution over the next observation. And similarly, a local reward function for an action gives you the reward. Going back to our example, this example is a regular decision process because it can be represented using this finite state transducer. Now, if I show you the same run as before, you can see what happens in the transducer. In particular, you can see that each cell, or most of the cells, have two corresponding states, not only one. In particular, each cell has a state for the case where the button has been pushed and a state for the case where the button has not been pushed. At the beginning, the button hasn't been pushed. And so we move along these white states, which capture the fact that the button has not been pushed. And then when we reach the button, we switch to the set of light blue states, and we keep being in these states. And so when we go back to the cell with the door, actually we are in the state where we are in the cell, but we are also in the state where we have pushed the button. So the door is open. Our main result is that reinforcement learning in regular decision processes is feasible in polynomial time. This result is based on the key observation that probabilistic deterministic finite automata correspond to regular decision processes under a fixed policy. And then we show PAC guarantees. So we show that there are probably approximately correct algorithms, reinforcement learning algorithms. And the guarantees are obtained by combining classic guarantees for reinforcement learning Markov decision processes together with the guarantees for learning PDFA, because PDFA are PAC learnable in certain parameters. So to conclude, what we have shown is that the notion of regularity yields a powerful perspective on non-Markov problems. In particular, so far it has allowed us to obtain polynomial time guarantees for reinforcement learning in non-Markov domains, and it has allowed us to identify and borrow from the literature a set of well-founded techniques to deal with non-Markov domains. Thank you.